What's going on, guys? In this video we are going to take a look at some recurrence relations. Let's look at the first one. The first one is Fibonacci sequence. Fibonacci sequence is basically it starts from 0 1 and after that the first two numbers adds up, like 0 plus 1, that 1, and then next two numbers adds up, 1 plus 1, that's 2, and then 2 plus 1, that's equal to 3, 3 plus 2, that's equal to 5, 5 plus 3, that's equal to 8, and it will extend like this. Okay, this is the Fibonacci series. Now let's see how can we express this one. To express this one, we can use it like an is equal to an minus 1. An minus 1 is 1 previous plus an minus 2. This is second previous, but here the first two terms always remain the same, 0 and 1. So first two terms we have to initialize, then we have to add the two terms because we need two terms to add up. So we always have to start from n is greater than or equal to 2, and the initial 2 we have to initialize a0, that is equal to 0, and a1 is equal to 1, and that's how the Fibonacci series goes. Now let's look at another recurrence relations. Here we have geometric progression. This is extending like 3, 6, 12, 24, 48. This is straightforward. You can see 3 times 2, 6, 6 times 2, 12, 12 times 2, 24, 25, 24 times 2, 48. Now let's see how can we express this one. So first we can say recurrent. This is easy to write. Recurrence relations is basically an is equal to the previous one multiplied by 2, because 3 times 2, 6, 6 times 2, 12. So we can write this one as an is equal to 2an minus 1, an minus 1, and then n has to be greater than or equal to 1 because we have to always have the initial one. Initial one we initialize, in this case that's 3. So we put a0 is equal to 3, and we after that we multiply everything by 2, and that's going to give us this series. Now let's say we have some situation like this. For example, if you want to find a667 using this one, you have to multiply a66 by 2. Now 666 by 2, and how to find a66? 666. To find this one, again you have to multiply 2 times a665. So there's no straight way to do that. But here you can use another analogy. Like if you carefully look at this one, like we can also write this one as an 3 times 2 power n. Okay, if you apply this one, this will still work because 2 power 1 times 3, that's 6. Okay, this is giving this one 2 power 2 for 4 times 3, 12. So there's another pattern like this. In this way it will be easier to calculate the bigger numbers, like this kind of situation easily. So we can put another formula for this one. An is equal to d, that's the initial one, times an minus 1, and a0 is equal to, actually a0 is equal to k, and n should be greater than or equal to 1. So we can express an as k times d is actually 2 here, not the initial one, d power n. Okay, so we can expand like this. N is greater than or equal to 0 in this case. Now let's look at a trickier example. Okay, here we go. Here we have 0, 2, 6, 12, 20, 30, 42. Now how to expand this one? Now here you can see a pattern that first we are adding 2, then we are adding 4, then after that we are adding 6, then after that we are adding 8, 10, 12, 14. So it increases, like we are increasing 2 and adding each time. Now let's see how to find a relation for this one. First of all, we can say a1 minus a0 is equal to 2, because if you subtract 2 minus 0, that's 2 here. And then a2 minus a1 is equal to 4. Then a3 minus a2 is equal to 6. And it's increasing by 2 times until it's an minus 1 is equal to 2n. So here what we are going to do is we are going to add them together, add all of them together, and see final results. The final result is going to be, here you can see A1, when you add this together, A1 cancels, and then A2 cancels, and A3, the next one will be cancelled with A3, and it will go like that, and finally you will also cancel this an minus 1. So the only thing that's going to remain is an and a0. So it will end up like an minus a0, that's going to be 2 plus 4 plus 6 plus 8 plus until 2n. Okay, now here we can do one more thing. We can take 2 common. If you do that, this is going to be 1 plus 2 plus so on, right? And it goes up to n. Now finally we can express it in terms of summation, like 2 is summation I starting from 1 to n I. Okay, in another term we can also write this one as 2 times n plus 1 divided by 2. So finally we will simplify this one into n times n plus 1, because 2 cancels, n times n plus 1. Now let's look at a number. Here we have the sixth number, that's 42. We have derived an equation for an minus a0. This is for an minus a0 because we extended this one. Now let's find an equation for an. So a0 is the first one is 0 in this case, so we can just eliminate a0 for this one. So that's going to be just n times n plus 1. Now let's look at an example. Here the sixth number, 1 2 3 4 5 1 2 actually it's starting from 0 0 1 2 3 4 5 6 6 is 42. A6 should be 42. Now let's plug in here. 6 times 6 plus 1, 6 times 7, that's 42. So we are getting a correct answer. So it's working. Okay, now let's look at another one. Whenever you have something like this, whenever you have an minus 1, that's equal to k, and the initial one is a0 is equal to c, and they have set a condition n is greater than or equal to 1. Whenever you see a situation like this, the general pattern is always going to be this one. An is equal to a0 plus summation of I is equal to 1 to n and k. It's always going to be like this. And this one we can also write this one as an is equal to actually an minus 1 is equal to 2n, and the initial one is a0, that's equal to 0, and n is greater than or equal to 1, and an is going to be equal to 0 plus summation of I starting from 1 to n, and then simply we can write this one as 2 times sigma I starting from 1 to n. Then we can write this one as 2 times n plus 1 divided by 2, that's equivalent to n times n plus 1. Okay, now let's try to prove this one. Okay, the proof is sigma I starting from 1 to n I is equal to n times n plus 1 divided by 2. Here initially, like if we write this one in terms of s, that's going to be 1 plus 2 plus 3 plus 4, it's going to go up to n. And also if we write this one in terms of otherwise, like other or in the reverse order, it's going to start from n and it's going to reduce 1 each time, and it's going to end in 1, right, if we reverse this one. So let's write in the reverse order, n minus 1 plus n minus 2 plus 1. If we add these two together, we are going to get 2s, that's equivalent to n plus 1, that's n plus 1, n minus 1 plus 2, that's going to be n plus 1 again, n plus 1 again, and n minus 2 plus 3, that's going to be n plus 1 again, n plus 1, and it's going to just go like that forever, like until the end. N plus 1, and these all are n. Okay, now we can express this n times. It's going to happen n times. Now we can express this as 2s is equal to n times n plus 1. So s is equal to n times n plus 1 divided by 2. So finally we can express this one as I starting from 1 to n, I, that's equal to n times n plus 1 divided by 2. And that's how we derived it. That's the proof. I hope you guys find this video helpful. Thanks for watching. And if you are trying to learn discrete mathematics, there are a bunch of videos in my playlist. I hope you guys watch that too. And don't forget to subscribe. See you next time.